How much introduction should I give to zero?
Zero.
Without further ado, Dave Bercovici will carry on with some of these surface ideas.
All right, can you hear me okay? All right. So after the talks over the past couple of days, I was wondering what's left for me to talk about. But I'm going to continue on a bit on what Hajid talked about yesterday with regard to interface physics. And well, let's just jump into some motivation and at least one color slide. There won't be too many of these. So actually, in a way, with regard to two-phase physics and what the point of this workshop is, melt in the mantle, I originally actually even got into this problem at all, not for wondering about melt in the mantle, but wondering about this issue of damage and trying to have localization of plate tectonics and whatnot, and I may or may not have time to talk about this at the end. But to do that involves sort of diving back into the two-phase physics equations that Dan really articulated very well 30-something years ago. But sort of focusing back again at the physics of what happens at the interface between the two phases, especially with regard to the surface energy, as we heard quite a bit about yesterday. So there's a bit that actually fell out of that. I probably won't even talk very much about any of this damage theory, and to some extent the damage with regard to interface between two phases, I don't know, that's been of marginal success. I mean, looking back now, it's okay for me to admit it, right, after all these papers on this thing. But I think more in terms of the grain scale physics, which I'll maybe touch on, but it's probably more relevant for the April workshop, which I won't be at. But I'll maybe mention it, okay? It depends on what timing I have, okay? So as we already heard about yesterday, the physics at the interface is incredibly important for understanding wetting and capillarity, and also self-separation, as even Sash alluded to briefly. Also with regard to a bit about nucleation, during melting or crystallization. As you know, there's sort of a nucleation barrier with regard to overcoming surface energy as you get a new melt or a new crystal to form. Pinning, which is important for grain growth, and I may or may not get to it, and damage, like I said, which I have doubts that I will get to. So I'm going to go into the details of how, from a continuum approach and trying to construct the equations that especially John and Mark sort of built up yesterday, and you're going to see a lot of the same equations, which is great. But how did we kind of reconstruct these while also considering the interface and the interfacial energy between these phases? So this is actually, I often call this the squash Dalmatian dog cartoon. Believe it or not, I hired an artist to make this. So I can believe I paid money for this thing. But anyway, it's been reused so many times for... So when we're looking at sort of the mixture of two phases, of course, we always think in terms of the volume fractions, and sometimes you think of it as porosity of one or the other phase. But we really wind up constructing this in sort of these mixture theories in terms of this thing called an existence function, or sometimes we've called it a distribution function. I'm going to grab some water while I'm doing this. And so to construct what the volume fraction is, it's very simply, the integral over the existence function for one of the phases, because the existence function is 1 in one phase, 0 in the other, and it's 1 minus the existence function and the integral of it to get the other volume fraction. And of course, we usually just refer to one of these as phi, okay, whatever you want, the porosity, and the other one is 1 minus phi, because they obviously have to add up to 1. And then we also introduced, and this is not, we did not invent this, these are things that were considered by others before, long before, people like me and Beckerman working in areas of metallurgy. This interfacial area density is something that you can write in terms of where the existence of the interface is. And the interface exists, of course, where the gradient of the existence function is, right? It is only non-zero at the boundary between this black and this white. And so, in a way, this absolute value of it is like a delta function, and the delta function locates the where the interface is. And then when you integrate over this basically gives you an area density, that is an area, interfacial area per unit volume within this control volume, okay? So that's a way that we've parameterized in a continuum sense what that interfacial area density is, okay? So I made a big deal about this one slide, but we'll see this recur several times. Okay, so to try to then figure out what the forces are, and the one thing I will note, let me back up one quick second, is that when we write down this interfacial area density, we make what's sometimes called, this is especially only true in two-phase media, not in two-phase multi-component media. that we sort of make what's called the Gibbs assumption, which is that the location of the interface is at such a point that it has no mass, okay? That as long as you have only two phases, you can put the interface in a particular position, that it has zero mass, but it has finite energy to it. When you have multi-components, you cannot make that assumption anymore because the different components have different, basically, locations of the interface. So they have a finite mass, as Ajit talked about yesterday. So when you're looking at the force balance of this, you can sort of just... Oh, yes, go ahead, please.
This gives you a concept of
zero mass.
you could also allow it to have a mass.
Of course, and that's...
They call it excess mass.
That's right,
And
sure.
then you can write it mass.
That's
balance.
right, and it's sort of an arbitrary assumption that you put it in such a place that all the mass is contained on either phase, on either side of the interface. Okay, so it's just a simplifying assumption, which we carried through. But it's something you can't do, like I said, when you have multi-component. Okay. Okay, so when you're looking at the force balance on some control volume that is arbitrarily cutting through various pores, okay, you of course, and these are not, I'm not going to look at everything, you'll see it in the final equation. Of course, you look at body forces, surface forces, but also the intersection of that arbitrary control volume with the interface itself, say wrapped around these individual bubbles. It doesn't matter which phase this is. Okay, the interface itself winds up pulling outwards. It's basically, in a way, the way surface forces act, that is the outside universe acting on this control volume, pushing on it with pressures and stresses. In the same sense, the outside universe of these interfaces are pulling, okay, outward on this control volume. Okay, and so there are line forces as well. So if you can imagine you know, if this was the face of one of your control volumes, I would worry about the line force of the intersection, you know, of this interface with the surface of the control volume. Say the surface tension line force, okay, again winds up acting like an effective pressure, because if we have more of these interfaces, say on this side, okay, a higher density of them on this side, they will wind up pulling, okay, to the right more than is being pulled to the left. So they wind up actually inducing what looks like a surface force, but it's basically an average over all the line forces on that surface. And that's really where that surface tension force comes from in a bulk sense, when I'm actually talking about the bulk force balance on the whole mixture, okay? But you make an assumption that the line density on the surfaces is comparable or is equal to, and this is something I spent too much time on, one of the first papers I did on this, is equal to the area, the interfacial area density. So in other words, the line density, okay, the line density per unit area is the same as the interfacial area per unit volume, okay? And there's some assumptions that go in behind that. So when you look at the net force equation, you have, of course, a pressure force, stress is acting on the surface, body force, and then you also wind up with something that looks like, almost like an effective pressure gradient due to these line forces yanking on either side of the control volume. And when I write down these barred variables, this is actually a sum over any one of these variables weighted by the volume fraction. So it's a volume average, okay? All right. What's that? Well, I'm sorry. Oh, I'm sorry. Yes, gamma is the surface tension. Okay, it's a force per unit length. Okay, or it could also be surface energy. Same thing. It's energy per unit area. Okay, all right. I mean, the truth of the matter is it isn't entirely true. This is really basically the conservative energy, okay, per unit area. There's actually a surface entropy as well, okay, which we often usually throw out. That depends on whether the surface tension, okay, this gamma is a function of temperature or not, which leads to the Marangoni effect. If you have that, you'll actually have a surface entropy as well. Okay, but we kept that in these original equations. We often just throw that away. Okay, it's not necessarily important for illustrating a lot of what we worry about, other than if you're doing Marangoni convection. Okay. Okay. So yeah, sure.
I don't think I understand how you define P bar, because surely the force balance matters whether the boundary intersects your
That's right.
regions or not, and that therefore P bar, if you define it just simply as the bulk average,
yeah,
that doesn't take any account of that difference.
The P bar, for example, is the well, I guess it's probably better.
But if it's defined as you've written it at the bottom, it doesn't take any account as to whether the outer boundary intersects the thing.
Yeah, it does. I mean, it's actually taking into account whether, I mean, this P bar is basically the average pressure over all of this. But this is actually another assumption that we often make in all of our two-phase equations, which is that the fraction of area taken up by a particular phase on the control volume is equal to the porosity. Okay, which is fine provided that the variation, say, of integrating over the over some thin slice against this boundary of the surface volume, okay, actually just varies linearly close to the boundary itself. Okay, so that way you can basically write down continuous gradients. Okay, so yeah, so this is basically the net pressure force acting on the whole thing, but it's basically the fluid pressure, for example, acting over this fluid surface, where this gray blob is intersecting the interface, and then the solid part or the other phase acting where the white part is intersecting. But again, you do have to be able to relate that area, the fraction of area on the surface of this volume, to the porosity itself. Okay. And it's doable, but you have to make some assumptions about how continuous your medium is. Okay, you have to say, and that really relies again on the continuum assumption that I've integrated over enough pores. So once we start integrating about not enough pores, then these things fall apart. But this is where two-phase physics is diciest, is when you don't have a statistically meaningful number of pores, just as it would be if you don't have a statistically meaningful number of atoms in your fluid. If we look at the body, surface, and interface interaction forces that we already heard a bit about from John and Mark, okay, they're written in the standard way, which we've got again, this would be the pressure force acting over one of the phases, the pressure on phase I acting over phase I, over that area of phase I, either fluid or solid in our case. The same with the stress tensor, the same with the body force. But then, as noted earlier, and John spent quite a bit of time talking about it, there's this interaction force, which is the body force, an effective body force between the two phases. Okay, that would normally just sum to zero by Newton's third law, that you have got to have equal and opposite forces between the two phases. However, when you have this interface between the two of them that doesn't sum to zero, if I sum this up, okay, over the phases, okay, this interaction force winds up having to be equal to this interfacial or the surface tension or interfacial area force acting over the previous volume. In other words, if I sum this equation up over I, it's got to recover this equation, which winds up leading to the idea that instead of these balancing out, I'm still left over with some force, okay, because the interface is acting as yet almost like another phase that's inducing a force, okay, distributed between the two other phases, okay. The interaction forces John and Mark, especially John, talked a bit about. It's the lowest order, has a Darcy drag type term to it, and this equilibrium pressure is something to allow equilibrium pressure in it. Of course, it has other terms in it too that Drew and Siegel illustrated. These giant number of terms that include things like the virtual mass effect and whatever if you're doing inertial terms. Okay, but we tend to throw those out in our viscous world. Okay, the surface tension force, we write it down individually. Okay, we say that there's a Darcy type drag. This pressure, sort of basically, this is supposed to be like an interfacial pressure, okay, acting against gradients and porosity, and that's just basically guarantees at an equilibrium. Okay, in other words, if I have a constant pressure, I'm not going to have a net force to it. Okay, whether or not, and Rich and John and I were just talking about this, whether or not this term includes the actual stress tensor itself, as was mentioned, is something we can definitely discuss. Okay, I have my doubts. I mean, there may be a point to it. I remember thinking about this at great length many years ago, and deciding, including those stress tensors, okay, these viscous stress tensors, is double dipping. Okay, counting viscous stress too many times, because in a way this is a parameterization for the viscous stresses acting on the interface. So I always worried about accounting for putting a full stress tensor in here instead of some pressure was going to be double counting stresses. Okay. With regard to the surface energy force, we assumed, okay, or we had to write down that it was weighted, in other words, distributed in some way between the two phases. So when they summed up, I would just be left with this term. And we originally thought, well, just to be fair, because we don't know any better, it's probably distributed according to the phase volume fraction. Well, that's probably wrong, okay? And it was actually Dan's suggestion that this is probably weighted more according to the strength of the material, which we then argued, yeah, that makes a lot more sense, because it probably the viscosity in a way, or the strength, is like a proxy for the dangling bond strength, how much surface energy tends to hang on to or is embedded or clipped to one of the phases or the other one. Okay, so if you have something that's a liquid and a solid, the surface energy tends to be more bound to the solid, which works much better. And in fact, this allows all these sorts of equations to recover pretty much identically Dan's equations. Okay, so let's move on. Okay, so I want you to remember we've already defined this delta V. You'll see this delta V as this sort of separation velocity multiple times. Okay, I was lazy and I just cut and paste this from another talk. So so there's a little bit of change in variable, but you guys will be used to this because we know that M is matrix, F is fluid. Okay, so normally I would be calling this P2 and P1, but this will be fast. Okay. I meant to redo this slide, but it got to be about 2 in the morning last night, and I thought, no, never mind. Okay. So in equilibrium, okay, so we can actually derive a lot of the relationships between the pressures. Okay, so we were always writing this as 2 different pressures, and we needed to have some constitutive law, as John pointed out, between the pressures. And you can go through this, okay, by writing down the second law, writing down the energy equation and looking at the entropy production terms. Okay, and you find that there is a part of the pressure difference in excess of what is being used to basically hold up against surface tension that has to go to some sort of viscous or dissipative work. And that winds up leading to a function that looks quite a bit like the bulk viscosity type term, okay, in excess of surface tension. So it's a difference between the pressures in excess of surface tension is going to be related to some sort of viscous behavior to it. And this B is very similar to something like the bulk viscosity, okay. You can also go, this would be like our damage attempts, okay, you can go a little bit further from, so in equilibrium, if there's no motion, then the 2 pressures wind up balancing against surface tension. If you're in something that involves actual compaction, then whatever in excess of surface tension causes compaction or dilation. You can go further and try to steal some energy from the deviatoric work to wind up doing some work on the interface. In other words, doing work to generate more interfacial area. I'm not really going to talk about that much now. This was a tough equation to work with for many years. And
Quasi-equilibrium, what does it mean?
this is basically saying it's moving slowly enough, okay, that it's pretty close. It's not exactly in equilibrium. It's still, you're still moving slowly enough, okay, but you're not like beating up and tearing apart the interfaces, okay. You're just allowing them to slowly compact and dilate, okay. So it's not, it's still sort of close to this, okay, but you're still allowing for some slow compaction and dilation. Oh yeah, so go ahead.
To say quasi-equilibrium because
No.
make a linear assumption there with dphi dt.
That's, part of the, this is part of the assumption in the sort of non-equilibrium thermodynamics that what you're really saying is that the product, of this sort of as a thermodynamic force, okay, against this dphi dt, which is like a flux, or you could make it the other way around. This has to be positive definite, has to be an entropy source. But then you make this linear, in non-equilibrium thermodynamics, you make this linear assumption, or this assumption that they're linearly related to each other. I mean, B can be a function of many things, but you still wind up writing these linear laws down, which, are really only valid in non-equilibrium thermodynamics pretty close to equilibrium. I mean, we know that, when you write down non-equilibrium thermodynamics for things like chemical reactions, they fail miserably because they don't obey like mass action, okay? So that's why we sort of say it's close to equilibrium, okay? Okay, so some applications, and you've seen, I'm sorry, a ton of equations blasting out at you, okay? But you've seen a lot of these already, okay, from yesterday. So just to make, what I want to illustrate with this is what's the general effect of putting in this surface tension force, okay? And so if we wind up looking at the mass conservation equation, that basically can start off as the mass conservation either phase. If I wind up saying, well, let's just define phi1, which would be like the fluid phase, or the minor phase is phi. We'll say the solid velocity is v, delta v is just this difference. So we can write this more simply in this way, and I write it this way because I'll wind up using this term in just a minute. So we can write mass conservation in terms of the separation velocity. If we look at the momentum equation, there's this bulk viscosity term. This B is sort of related to the bulk viscosity. It's got some factors of 1 minus phi in there, but let's not worry about that. Just remember B stands for bulk viscosity, okay, of some sort, or some function of that. You have the deviatoric stress, the Darcy drag, and then you have this extra term. Oh, I thought I had put a square in it, but I do have this extra term here that involves the second derivative, okay, well, it's really the gradient of d alpha d phi, okay? Now, one thing I should point out, let's go back a slide. This d alpha d phi, if you haven't noticed already, I didn't emphasize it enough, by writing down what's called really the Laplace condition, which balances the pressure difference across either side of an interface against the surface tension, is this d alpha d phi is a way of writing down curvature. It's like a mean curvature across the mixture. It's not a local curvature. It's basically as if you had took the average curvature across this mixture, but it only exists on the interface. Remember that, okay? So this d alpha d phi is like a curvature. So this winds up being like a gradient of d alpha d phi. If we assume it's just a function of phi, then you wind up with a second derivative, and this turns out to be important. But this is like this effective pressure, okay? The surface tension acts like an effective pressure, and you wind up with equations that are quite similar to Hajid's equations, where we've got a Darcy flux balancing against this thing that has these capillary forces to it, but also you wind up having these dynamic terms that have to do with compaction and deviatoric stresses, okay? So you could sort of relate those, okay? Now, if we take the long wavelength assumption, just for simplicity, just to illustrate this, okay, which says that these terms will go away, so you're kind of way beyond the compaction length, and I worry about the balance between the Darcy drag and the surface tension forces, I wind up with a rather simple-looking velocity, a separation velocity like this, okay, which I can then dump into this equation here, and I wind up with a diffusion equation, okay? Well, it's effectively like a diffusion equation. So this big D here, this diffusion, winds up going as this second derivative of this alpha. We'll talk about this more in a minute. So what D is, okay, this diffusivity of how porosity winds up being, or how the fluid, okay, this phi now represents the volume fraction of the fluid. How it gets distributed depends upon what the sort of curvature is of this alpha, okay? And if we assume, okay, in our simplest, in our original versions, okay, we said, well, it's sensible to say that alpha, the interfacial area density, should vanish if I have all one phase or the other phase. So if phi goes to 0, it should be 0. If phi goes to 1, it should be 0. And you wind up with this sort of downward curving, almost parabolic type looking function here. Well, this winds up giving you a negative curvature, okay, and it leads to this thing called self-separation, okay? So if it's a negative curvature, then this would be a negative diffusivity, which mathematicians hate because it just leans to singular, instead of spreading things out, you wind up with a bunch of singularities. But that's what you would get in terms of self-separation. If I have oil and water or sills or something else like that, the phases will tend to separate into one phase or the other, okay? And so you wind up collecting phases instead of spreading them out, okay, like oil and water. But for silicate melts, this is probably wrong, okay? That we probably more would like to see that this alpha, this interfacial area, does not just vanish, but it actually goes to a finite value as I go to 0 fluid, because I have grain boundaries. I have grain boundaries that still wind up having some effective surface energy, some effective interface still floating around in there, even as I wind up going down to almost 0 porosity, okay? And this is something that Sash worked on when for his year and a half or so at Yale, okay, trying to find from sort of micromechanical models, what does this alpha wind up looking like as I go from something like the suspended, say, crystals in a melt, as the crystals grow and wind up going into sort of dihedral angle contact with each other. And you wind up getting something more like a function like this with an upward curvature, which is great because if it's an upward curvature, this means that diffusivity or the diffusion equation is a positive diffusivity, and you wind up diffusing fluids outwards. So you wind up getting sponging or wetting instead in the sort of continuum model. Okay. What's that? It doesn't go to infinity. Okay. Well, because you wind up limiting, the final limit is what the net interfacial area is of all the grain boundaries. Okay. So it's not like you've gone down to an infinite number of interfaces. Okay. It's basically modeling if you've gone to a finite number of grain boundaries. Okay.
But if you have melts at triple junctions, then the curvature goes, and it goes singular because the radius of curvature becomes 0.
Oh yeah, yes.
So
You're right. I mean, you're thinking this is just alpha. The curvatures do go to infinity. Okay, if that's what you're thinking about. This is not the curve. This is just the density of interface. Yeah, Jerome. Sorry, I'm not sure Dan's happy with my answer.
No, I have 3 different questions. One is, does alpha have to be monotonic?
I don't know. What are you thinking? I don't.
Well, that was purely speculative, just because you could get something that looked like it was going to 0, but then went up to a finite value. So you could get both diffusive effects and
I mean, you want to have like a, you want an alpha that looks like a hysteresis curve or something?
Sure, that was just a purely speculative comment.
You should
But
follow that through.
the other thing is, doesn't this rely on your assumption that the permeability is finite at all points to get yourself to the diffusion equation?
Yes, it does.
Okay.
Okay, but you remember one thing, I should, none of us have stated this yet, that when we write down these mixture laws, and we might have been, we might have homogenizing or doing these averaging over all of these equations, we assume, and not always very well, okay, that these phases are always interconnected, okay, that they're continuously connected with each other somehow. But then we wind up also, once in a while to understand things like interfacial area, we say, well, let's make it's all bubbles. Okay, well, that means one phase is connected, but the other one is not, okay? So there's a lot of, sometimes you have to understand this by looking at sort of, because one of the greatest difficulties with two-phase physics is just we don't know what is going on at the interface because it depends on the topology of the interface. It could be tubes, spheres, packed, solids. It could be any number of things. So we don't know, and we wind up writing down sort of these, knowing anything about this alpha depends upon the topology of this interface. So we kind of write down what we think are sensible equations, but there's a lot that's lost in there. And when you write down the permeability equation, it's the same problem. The permeability law depends on the topology of the interface. And I've always said that the permeability itself is a parameterization of that interfacial topology, whether it's tubes, spheres, etc. Okay, it tells you whether it's phi to the squared, phi cubed, or some other complicated function. What are your other 5 questions?
So that we can be here all morning.
Yeah.
The last
right.
question was, your alpha is essentially for a monodisperse media at the moment.
Yes, that's
Do
probably.
you think that would change this sort of result drastically if you said, actually, there's a range of alphas, there's a distribution of, if you took not just the mean, but the next moment, for example, into account?
Good question. I'm staying out of the way of the camera, so I can't see my. Okay.
But I don't
Yeah.
agree with what you've said because the geometry of the melt in equilibrium
Which part? What don't you agree with?
determines the shape of both determines the shape of the solid and the shape of the liquid. Right? And so, you can indeed work out what happens on a grain scale simply from the dihedral angle.
Yeah. Okay.
And you shouldn't assume that these things are spheres, and you shouldn't say that we don't know what it is. We do know what it is.
Yeah.
It consists of these filaments along the grain edges with junctions where 4 of them meet. So you can actually do all the calculations for these
Yeah.
channels along the grain
I mean,
edges.
this is in fact what Stosh did, okay, to try to improve on what we had assumed earlier, because this assumed nothing about geometry. What he tried to do is look at the case of, if I go to something that's more like a suspension, okay, in which the grains are not in contact, to the point where the grains grow big enough that they are in contact along these dihedral angles that wind up looking more like these tubes, okay? And then extending it further to say that even when you're down to, almost no fluid left, you still have some interfacial area left. So you're completely right. But this is for our favorite melts, right? For these silicate melts that wind up having these behaviors to it. So Rich looks like he's building a question behind you. So.
I'm thinking about how you have multiple solid phases.
Mm-hmm.
And, when I've seen even the olivine melt X-ray tomographs from Wenliu, they never really look like textural equilibrium in an ideal sense. But maybe
Well, that's because you can't see it. The resolution of the X-rays is not sufficient to see what's happening actually at the rainbow. You really have to do it by transmission.
Oh, okay. Well,
But
but this is fine. But
there's a point. But what you're trying to do, which I can't see is going to work, is to produce one theory which will deal with the whole range of phi. I mean, the physics is completely different. Right? Once the grains become suspended from when they're in contact and you've got a small amount of melt. And I can't see why you think you should use one theory to go right across that range.
well, I mean, yes, you're actually right, because it turns out that as you go to that contact, there's sort of a discontinuity in this alpha that winds up occurring, right? And so we kind of fudged over that, but that's true, because you do wind up with two different interactions between these solids and the melts as you kind of go from suspension to something that's dihedral angle. So, it's quite true. I mean, this may be a failure of trying to capture this alpha over these large ranges, okay? But with regard to, whether it's, do we know everything about all interfaces? I mean, it's, for these sort of silicate melts, I mean, it could be diapers or any number of other sorts of general applications, packed, granular media, any number of things. So this is our best attempt. But there are certainly failures to it. I don't deny that. Okay, yeah.
So this alpha is measuring the amount of, say, fluid solid spatial area.
Yeah.
And you're saying it can't go to zero when the porosity goes to zero because you still have this surface area between the grain boundaries of the solid.
Right.
But surely that's a surface area that you should count separately. And so in your force balance, that should have a different interfacial energy associated with it and everything.
That's right. So actually, I mean, I'm glossing over it a bit. What Sasha's paper originally said is we wind up basically combining the interfacial area and energy, okay, into one term. And what he was really saying is that the interfacial energy, okay, goes from, what exists on this interface, and then when you transition to something that's just grain boundaries, it still exists, okay, over some distribution. So I wanted to sort of glomming together the idea of this energy and the interface together. So that's very true. But I'm trying to sweep all these together, okay?
Maybe you shouldn't say alpha never goes to zero. If phi is actually zero, alpha will be zero. Absolute zero, absolute zero. It's just that I guess you're saying you're asymptotically approaching porosity of zero. It will never be zero.
Well, this is a,
If it is zero, then you have indeed other equations.
yeah. I mean, this is what my answer to Chris's question also is that, when we tried to treat this as it going to these grain boundaries, you really have to look at the energy on the interface, okay? That's the thing that does not go to zero. Okay. All right. So really, when we were plotting, so there's a bit of a, again, to try to sweep things together. In Sasha's type work, this alpha would really be more like a gamma alpha, okay? This dash curve. Okay, we okay? Can I go on to slide 3? All right, it's 4. I don't know. Okay.
If you don't include solid surface energy, you can't have a dihedral angle. You can't self-consistently model the geometry.
That's right, but that's what we were doing before. Okay, in other words, that's why we were including both of them sort of combined together into this interfacial area times the energy. So that's the only way we could calculate this dihedral angle, is including that solid energy. Okay, which is what Sasha said. Okay. All right, let me keep going. So there was one aspect. Well, let me see how we're doing on time. 20 minutes? Okay, yeah. Let me just mention this very, very, very briefly, okay, because I wanted to get onto some other things. I'm certainly not going to have time to do any of the grain course thing, but that's okay. If we actually look at this problem with regard to simultaneous melting and compaction at the same time, we wind up going through the same exercise but allowing for this delta gamma term between the two mass conservation laws, which John talked about yesterday in the exchange of mass between the two of them, and you wind up with these pressure in excess of surface tension, and pardon me, the sigma, I cut and paste this from a paper. The sigma is really the surface tension, so sigma is gamma, okay, in this cut and paste. So I hope that doesn't confuse you too much. Okay, that it winds up being also related to the compaction rate in excess of the mass exchange between the two fluids. Okay, and in addition, the exchange rate winds up being sort of this in excess of equilibrium. Okay, these delta E's are the exchange of internal energy. The delta S is exchange or the difference in entropy between the phases, etc. Okay, and also the effect of surface tension on that equilibrium curve. So this is basically like you can turn this into a Clapeyron slope. If I say it's close to equilibrium, that says that the delta gamma over this L22 is like one of these phenomenological coefficients. It doesn't really matter. You get a Clapeyron slope, and the only important part of it is this, is that you get this term here that winds up acting like the effective surface tension on a phase boundary. Okay, that winds up, for example, leading to, in very, very small porosities, like a nucleation term. Okay, so you have to wind up exceeding, or you have to winds up adding to the pressure, so you have to actually increase the temperature that much more to wind up causing the very, very first melt if you have the surface tension term available. Okay, but we don't have time for that. I'm going to probably wind up spending the most of the time on this newest stuff that John and I did recently. And you may, if you didn't like the last of this, you probably hate this. Okay, this is way out there. Okay, but it'll be fun. You guys can have fun beating me up over this. Okay, John, should leave John alone. So we were trying to look at this problem of diffuse of melt shear bands. Okay, and as was talked about yesterday a few times, when you look at these very nice experiments done by Ben Holtzman and Dave Kolstedt and others, that in partial melt and shear, you wind up getting these bands, and these bands wind up developing these melt bands that are of the order of a few microns, 1 to 10 microns, separated by a larger length. Okay, but they always wind up going to some finite shear band width and separation width. But the theories that lots of people have put out, okay, that we've all sort of acknowledged that they all have this problem. They all wind up growing at the maximum wave number, or the smallest wavelength. So they wind up growing only when the shear bands go to 0. So it's been a problem with regard also to numerical modeling of these. As you heard people refer to these melt bands dropping down to the grid scale. You just can't seem to resolve them. So John and I set out trying to resolve this in the simplest manner we could. Okay, may have just caused more problems, but by considering basically liberally ripping off from what's called phase field theory. Okay, in phase field theory, you wind up treating the interface, or you wind up treating the two phases of a medium as if they're two, it's a continuous function, and the gradient of that function represents the interface between those phases. Well, we sort of mixed two-phase physics with phase field theory in a way, in which we're allowing for a thing called, we're calling a diffuse interface effect. So the interface, the interface only for a smooth distribution of pores and matrix, okay, you probably will hate my spherical pores, but it's an easy model to deal with, okay, just winds up only existing where there is this microscopic interface where between, say, the bubbles of fluid and the solid, or the grains of solid and the fluid, doesn't really matter which one. Okay, but at a very sharp gradient in the porosity, that gradient can start to act like another interface, but it's only for very sharp gradients that it really starts to kick in. At least that's our hypothesis. For example, if I have a very dense collection of bubbles, okay, if I have, say, one big spherical blob that's filled with a lot of bubbles, okay, that dense collection of bubbles can now start to look like a big bubble in itself, okay, and that big bubble will look like it has its own interface with its own surface tension on it, but that will be delineated by the gradient in this porosity. Okay, so the derivation of this, which I'll go through just so you can look under the hood a little bit, okay, of how we wind up going through this, is not, it's more heuristic, okay? I mean, John and I went back and forth trying to get some really rigorous mathematical derivation, but the best we could come up with is this sort of heuristic argument. A lot of this involved my throwing some stupid idea out and John going, no. Okay, and then I'd throw another bad idea out and John would go, no. Okay, all right, but back and forth enough, we eventually came up with this argument. Okay, again, we go back to this existence function, okay, that locally will just wind up giving me, in a way, the interfacial area density for the microscopic interfaces. So there'd be this A instead of the alpha. We'll get back to the alpha in a second. Again, it's where the interface exists by taking the gradient of this existence function, which is again between 0 and 1, one phase or the other. And we also define the volume average of it, so we can use this later in terms of these brackets, okay, these angle brackets. Okay, the interfacial unit normal, the local unit normal on that interface, okay, pointing, say, away from phase 1, the fluid, into the matrix phase, is again just going to be the gradient of this existence function divided by its, or just normalized, okay? And if we want to look at the curvature, it's the divergence of this unit vector. It's the definition of curvature in an interface. Okay, winds up looking like this term, a Laplacian of the existence function and a gradient normal to the interface itself, okay, defined this way. Okay, so it's basically again, the gradient exactly normal to what the interface is doing. Okay, so then we want to look at the mean curvature, which is something that we more want to deal with. We will wind up talking about it being d alpha d phi again down here. You wind up averaging, and this is something that was really a method devised by Sun and Beckerman. This fellow Beckerman has done a lot of rather nice papers on this, and they were actually really using phase field theory. So again, we're kind of ripping off from that. the mean curvature is defined as a volume average, but on the interface itself, okay? So it winds up being just defined so that it only exists on the interface, and you wind up writing it in this term, that this volume fraction of this thing is just A, it's the interfacial area density, and then you have the volume average of these two terms that came out from the local curvature. So our heuristic argument was this, that at the microscopic level, individual bubbles, for example, the contribution is really only the second term. Okay, so for n bubbles, okay, our spherical bubbles, radius A, the interfacial area is just the, the net surface area of these bubbles divided by the volume. Okay, but you can also wind up showing that the average of the Laplacian is 0, but the second derivative normal to the interface is 8 pi a, and so actually these wind up giving you just a rather standard curvature. If I take this term divided by 1 over a, it just gives you 2 over a, okay, which is the standard Gaussian curvature on a sphere. Okay, near a coherent structure, and this requires a little bit of explanation, if I have a coherent structure like that diffuse interface, like this drawing here, what I mean by a coherent structure is something like that, okay, near a coherent structure with a sharp gradient, the Laplacian of theta turns out, you can show, and so did Sun and Beckerman, that it winds up being the Laplacian of the porosity. And the second derivative normal to the interface, we argue, is 0. And the reason we argue it's 0 is if my control volume is small enough that that coherent structure in that control volume is flat and straight, okay, this second derivative is an odd function, okay? The first derivative is like a delta function. The second derivative is like 2 lobes on either side of it, so it's an odd function. So we integrate over that. The only place that it exists, those 2 lobes on either side, taking the derivative of a delta function, cancel out. So it's 0. Okay, so that means that one term, okay, this term here represents the curvature, say, on the diffuse interface. This term represents the microscopic curvature from the bubbles. You add them up, and we wind up having this an adjusted type curvature on the interface that accounts for the microscopic curvature and then this curvature from a diffuse interface, okay? And you may really hate that, but it's something also seen from the sort of phase field theory from Sun and Beckerman, but they throw out the microscopic interface term. We like to hang on to it to allow for things like capillarity. All right, so if we take it and drop it into the same equations we used before, mass, something that looks like Darcy's law for just a fluid, bulk viscosity, deviatoric stress, separation or Darcy drag, and then we also have this term here, okay, which should really be originally written as a gradient of d alpha d phi, okay? So this is like this effective pressure due to surface tension. Now, this diffuse interface effect winds up leading to a couple of, an important term. One is, let me point this out, we'll go back one, that this is just the local curvature due to the microscopic structure, and that would wind up leading to a pressure due to capillary forces, which we already saw, either causing wetting or self-separation, okay? This other effect here winds up being an effective pressure due to the curvature, okay, the curvature of the porosity itself. So you imagine if I have a porosity, high porosity, it's like a Gaussian shape to it, it's like a bubble, okay, that it winds up being like a high pressure term that pushes fluid outward. So it winds up smoothing things away. So that's how this term will wind up acting as an effective pressure where there is a very sharp curvature in the porosity, okay. One thing to point out, this is, if I'm looking at two-phase medium that's well mixed, this is a big term, okay. This A is big, okay, relative to, other types of interfacial areas that we might consider like on a diffuse interface. There's lots of bubbles if we're actually averaging over many. So this is a big term, so this only really kicks in when this term here becomes large enough, it's sharp enough gradients, okay? All right, so if we drop that in here, and then we allow for a lot of things that Rich did in his thesis, looking at the effect of shear bands with very strongly variable viscosity that's porosity dependent, non-Newtonian, okay, then we wind up prescribing a shear, we wind up linearizing as usual. We do what Mark introduced before, this Helmholtz introduction of a Helmholtz relationship. In addition to the shear, you have sort of a compaction or a potential flow that allows for compactive or compressible flow, a solenoidal function that winds up allowing for any type of circulation and shear, okay, And then, of course, we have a linearized, this is a viscosity function term down here that allows for how viscosity depends upon these perturbations. Okay, so we already saw that. Yes, I'm going super fast because I got, yeah, go ahead.
It's clear why you put gamma in front of the microscopic curvature term.
Yes.
Why do you put it in front of the...
This
Yeah.
one?
I mean, it's clear why it sits
Oh.
in front of dAd5, but it's less clear, at least to me, why it sits over in front of 1 over a, your second term.
Yeah, I mean, it's basically the same, you know, there's only, I mean, in this model, there's only the one surface energy that's accounted for. But these are, remember, these are kind of distributions over these, you know, only this, even the diffuse interface only exists by virtue of the fact that there's this interface between the two of them, okay? So it only has that same energy to it, okay? So it's not, we're not assuming that there's a different energy associated with a diffuse interface. I guess you could, okay? That's another ball of wax or something, okay? Okay, keep going fast. This is about as much as we'll get into it. Okay, again, these linear equations, you know, what's important about it is basically this term. This is the term that winds up introducing these capillary forces to it. This factor here is just the capillary effect itself of microscopic curvature. This del fourth term with this big D here allows for this diffuse interface effect. Okay, that's the important term here. That's the important difference. Okay, you throw all of these away with a big, you know, this everything multiplied by the big gamma, which is relating to anything relating to the surface tension. Okay, you'll come back to equations that look a lot like Rich's from 2006, right, Rich? Yeah. Okay, so that's what's most important. Okay, and then you have these different non-dimensional parameters: the ratio of shear viscosity to effectively a bulk plus the shear viscosity. This term allows for the surface tension effect with some curvature. This big D here is what parameterizes the diffuse interface effect. Okay. You, again, linearize with this wave vector that depends upon a wave angle. You come up with an expression that looks a lot like what Rich did, except for this one extra factor here, which is due to the surface energy terms. This big D, again, is related to the diffuse interface effect. And what we found is that if we throw away this term, okay, we will always find that if D is 0, as the wave number goes off to infinity, then the growth rate will just flatten out. It'll just go to some constant asymptotic value. It doesn't go to a selected mode. But you can see if D is finite and this K goes to infinity, you know, it's hard to look at this equation in total and get this, but as K goes to infinity, the growth rate will drop off to negative infinity. It's a lot easier to just look at some cute diagrams, putting some color in here finally for your sake. Okay, different colors too, okay. So for D is 0, no diffuse interface effect. This is the wave number, this is the growth rate, this is the angle. You see what the angle as, and there's nothing new with regard to predicting where the angles of the shear bands occur. These are, if it's non-Newtonian enough, these are at around 20 degrees with a conjugate, okay, as Rich already found out. There's nothing new with regard to that. Okay, but if you have no diffuse interface effect, even with a capillary force, you get no selected mode. Okay, the growth rate just goes off, and this is truncated, so it just keeps going off and off. But with a diffuse interface effect, there is the rollover. Okay, there's a rollover of the growth rate, and you do wind up picking up a peak growth rate. So the selected mode, the wave number for the maximum growth rate at the maximum angle goes as these dimensionless numbers Q over D. Okay, let's not worry about this, but it does depend upon what D is. It winds up being a very big number, even non-dimensionally. The growth rate at the maximum isn't any different. Okay, that didn't change at all from what really Rich could infer. Okay, but what was important is you wind up getting this rollover that gives you this selected mode. Now we compare this to a couple of experiments, one with a large compaction length, one with a shorter compaction length. We wind up doing a pretty good job. Okay, when we put this in terms of wavelength, and then you cut the wavelength in half to basically give you what the bandwidth is, or the melt bandwidth, we do a pretty good job of predicting a very small melt bandwidth. Okay, because again, this K winds up being a very big number. You can even go back here, okay, and find that, you know, these are modest values. Okay, but if you go off here to log 10, say like 100, could be even more like 1,000 if we use even more. You know, bigger values of Q, smaller values of the big D. What's important is that the K is big, the wavelength is small. It wind up predicting these bands of about 20 microns for the experiments with a large compaction length, which is about what they see. I mean, our wavelength was about 40. They see a bandwidth of about 20. For the small compaction length, they see a few microns. We see a few microns, only 2. Okay, we have a wavelength of about 4. Okay, that's just for the melt bandwidth. We do not predict the spacing, which is a bit larger. The spacing tends to be about an order of magnitude bigger than the melt bandwidths themselves. Okay, they're probably more typical of the compaction length, and so we speculated because we can't get the 2 wavelengths. Okay, it's not like a mushy convection problem that Gray, Worcester, and others have worked on, where you get 2 different wavelengths predicted out of the linear problem. We only get 1 wavelength, 1 mode out of the linear problem. Okay, so we don't get the band spacing, but we sort of speculate that as the melt bands form in more of a nonlinear regime, they wind up having to draw melt away from the surrounding solid, and they can only draw melt away from a compaction length. Okay, and therefore that's why we would speculate that this band spacing, okay, like the green areas, are more typical of the compaction length because that's where you have to draw fluid away from. Okay. Was there anything else I wanted to say on this? No, there's all this grain dynamic stuff. I figured I would never get to this, but in case by some miracle I went through this other stuff faster, I would have done it. Okay, but I'm not. Okay, so we can just leave it here and take some questions.
Questions for Dave?
We had a fair number, but yeah, Mark.
Okay, so yeah, what you're actually just following up on what you last said. I mean, the actual selection, certainly in the computations, is the nonlinear one at the end. Eventually, you compact between.
Yeah.
The linear analysis only tells you the initial instability,
Right.
but what actually gets and they don't actually go to the grain size. I mean, they don't go to the mesh size. They actually look like solitary waves, but they have a finite size. Well, they compact between them. They don't go to infinity because they run out of melt.
Oh, I see what you're saying.
Where they blow up is usually because the porosity goes to 0 between them, which is what doesn't happen in the experiment.
Yeah.
So there is a nonlinear selection of bands by basically compacting out the melt.
Yeah, there are other, certainly this is one of them. There's that. I know Sam Butler has argued that, you sort of wind up rotating out of the maximum growth angle before you wind up getting to that point. Because, once you rotate out of the 20 degrees, you're beyond the maximum growth rate. And, I know Takai over there and Sasha had another argument that it's basically related to chemical reactions. So if there's a diffusion term in terms of chemical reactions. I mean, I know Ben was trying to get melt bands that were non-chemical, but whether there's actual chemical reactions or not, I don't know. Go ahead. Mark.
One more question. Just I'm just a little unclear how you say you're getting the band width.
It's impossible to hear. Can you repeat?
Oh, yeah. Do you have a microphone? Mark, then you can stand up and shout.
I'll stand sideways so we can radiate this.
Yeah, that's fine.
So I just don't quite understand how you're predicting a band width. Again, to the linear analysis, you're finding, harmonic.
We're finding one. Yeah.
You're right, but the shape of the actual melt bands is they're flat topped. I mean, they have a width. They're sort of flat topped, and they have sharp.
You're talking about the band or the space or
the melting. The melt
melting.
bands themselves look like, if you look at the pictures, they look. There's a local where they have a maximum porosity in them that doesn't vary that much, and then they have these sort of sharp edges on them.
Yeah, it's your.
I just don't say you get that. Out of
no, but that's you've answered your own question. I mean, it's a nonlinear effect once you've actually drawn out the melt and at that limit. I mean, all we're saying is that the initial instability is sort of maximize. This is way at the beginning, of course, of the experiments. You're selecting at these small modes. Okay.
Yeah. Well, so you're picking a wavelength of the fastest growing thing, but I don't see how that gives you a band.
Yeah. I mean, this is all we're saying is that this. If you look at the selected mode, okay. I mean, as I say here, it does okay. Yeah, the slide. It does okay at predicting, or at least being at the same scale of the band width. Okay, but it would fail at trying to predict the band spacing. So it's only getting one of them, or neither of them, if you want to put it that way, if you prefer.
I just think it's just questions slightly apples and oranges.
No, it's. I mean, if these are original perturbations that are growing, okay. I mean, we would interpret that the band spacing is something more along that nonlinear regime, where you're basically having to draw out from this compaction length once you have a finite amount of melt in the bands, in the melt bands themselves.
Funny, I would actually have picked that as being the band spacing. It's the fastest growing mode, those are the peaks. That's where the bands are going to be.
Well, those are
That's
the spacing is where the troughs are.
whatever.
I mean, I'm sorry.
it's, a,
Okay.
it's a harmonic.
Okay.
Whatever.
Done.
Or,
I mean, the basic argument is the basic argument is that the surface forces matter. So the obvious thing to do is to do this same experiment with different surface forces, which is quite easy to do because if you use a carbonate, right, that lowers the surface energy hugely, right, because we know that from the dihedral angle. So that should then lead, if you keep everything else the same, it should lead to a different spacing. Has anyone tried that?
Need to talk to Dave Colstead.
Yeah, right, I know.
They have done experiments with different liquids. I don't know if they've used carbonate, but they've used different.
You need to use something which has a very different surface energy.
I mean, is it possible?
If you think it's a surface
I
energy.
mean, Rich, you would know. Is it possible? I'm not sure that Dave and Ben have the information on the surface energy for all the experiments they already did. Maybe there's enough variation in those to test it.
We have some things with different silicates.
Yeah, right. I mean, we even look at these, but I don't know if these surface energies are significant enough between these media to. I don't know. I don't know what that is because typically surface energy doesn't change. Well, Dan, what do you think? I mean, surface energy is typically of order 1, but how much variation in these other, would you say these carbonates? Is that what you were?
Yeah, the dihedral angle in the carbonates is 15 or 20 degrees compared with something like 40 degrees for the things on this list.
Okay, that's it. Yeah.
Rich, I just want to disagree with what you said about the growth rate as a function of wavelength. I think below the compaction length it flattens out, and so you don't necessarily get the smallest wavelengths growing fastest. You get
You'd like
Yeah,
one
it's like below the compaction length.
sorry.
go ahead. I'm sorry.
You don't necessarily get the smallest wavelengths growing fastest. You get the wavelengths that you've seeded the calculation with. I mean, if you seed with white noise, then you may end up getting the smallest ones growing. But if you seed with filtered white noise, then you may get the smallest wavelength that you haven't filtered.
Are you talking about in the case?
Initial conditions.
But you're talking about the case without any of these surface tension effects. I mean,
Right.
you're talking about basically this curve.
Yeah, I'm talking about that curve without surface tensions. Agreed. Yeah, I mean that changes when you add surface. But
then you've
you
got to
don't- you
choose
don't
what
necessarily-
frequencies you put in to begin with, and you'll
Yeah,
compare whatever.
but that's right. It just becomes
Yeah, no,
it's initial condition dependent in the end, right?
yeah,
Yeah.
absolutely.
It's certainly true in normal calculations, but
But there isn't the problem that this curve slopes upwards with K. It's
Yeah.
flat.
yeah. Okay, we've gone
Okay,
over.
I guess we should move on.
You want to swap out computers? Right?
Yeah, cool.